edition of Last Minute Panic. I'm your host, Mr. Brown. Next slide is all about searching and sorting algorithms. Now, I'm trying to explain them one at a time as best we can, but overall, I am looking for you to take away 2 searching algorithms and about 3 sorting algorithms. Right? Searching for information, sorting information, that's all the difference is. Right, our first is a searching algorithm. So we're searching for information. It's called a linear search. So we start it at the very beginning of the data set. So we start here at the position. Alright, we start looking for a value. Now in our case we're going to look for the value of 10. And we start at the furthest point to the left and we say, does that, it's 20, sorry. We'll look, does that value equal 20? Does this equal 20? If it doesn't, we cast it and we move on. Does this value equal 20? It doesn't. We cast it, we move on. And we move through the list one at a time until eventually we either hit the end, in which case the value is not in the list, so there is not in the list, or we find our value, in which case we have successfully searched the dataset. And that's how a linear search works. It's really easy to program, it's nice and organized and simple, but it's really, really slow if you've got a really big list. Next one is a binary search. So a binary search means the data has to be in order. That is vital. You have to know this. So the data has to be in order because a binary search works by splitting the list in half so that some numbers are on this side and some numbers are on this side. Now if the numbers aren't in order, that split doesn't make any sense. So I'll rub that out. What binary search does is it takes your list and it tries to find the middle point, say here. There you go, like that. And it looks at the value and it says, is it bigger or smaller than the value in the middle? So is it bigger or smaller than, in this case, look, 16. So if we're looking for the number 20, say, or 23, sorry, I should say. Well, it's bigger than the value in the middle, 16. So what it does is it says, well, ignore those. That's half of the list then that we don't have to compare. So from then on, look, it's just ignoring that half of the list completely. So there's no comparisons then with the other numbers in that list. So there are fewer comparisons in a binary list, usually. What it then does is it moves to the half of this list. So it finds the half point in the new half, so basically the quarter point. And it compares the value again. Is it bigger or smaller than 56? And the number we're looking for is 23, so let's just say it is smaller than 56. Therefore, we go to the left, which means these numbers to the right, we can just completely ignore because that value is not going to be in that half of our list. We then go half again, so now we're in here. Is the value bigger or smaller than 23? Well, it is 23. That's the value we're looking for, in which case we found it. So the value was in this. If it's not, it will just keep going until eventually there are no numbers left to test and it says the value is not in the list. But that's a binary search. It's all about splitting the list into 2 as many times as we can and basically saying if it's bigger, we only focus on the right half. If it's smaller, we only focus on the left half. So that's the way it works and we just keep splitting it. And that's a binary search. Next one is a bubble sort. So a sorting algorithm is all about organizing a list. So if a list is all in a mess, we use a sorting algorithm to sort. The first one is a bubble sort. Basically, we look at 2 values in a list. We start at the furthest left 2 values and we move them. That's kind of it. So the biggest value is moved to the right and the smallest value is moved to the left. We then move to the same here, like that. And we compare those 2 values and we move them into order. And then it'll move to this one, these 2, and then these 2, and so on and so forth, comparing all the values. What it'll then do is it'll repeat this process boop, the same way until no swaps are made. So it's basically taking, in theory, all of the different numbers out in what it calls a bubble. So it takes these 2 out into its own little bubble to compare them and then switch them around if it needs to. So it swaps them about or leave them the same if they're in the right order currently. And it works through the list. Now every time it goes through the list like this, it's called a pass. So every one time through that list is a pass. Once it makes no changes, so like this one, it'll go through it. Is 2 bigger than 4? No, so leave them the same. Is 4 bigger than 6? No. So compare, no swap, compare, no swap, compare, no swap, compare, no swap. That means we've been all the way through this data set without any changes. So that pass required no changes. It means that the data is then in order. So that's a bubble sort. The next one is a merge sort. The way this works is that divide and conquer idea. So we take our list here and we break it down into smaller groups like that. So we divide them down like that. We divide them until we've got them into individual numbers. And the idea then is basically to try and organize those individual numbers. So then we start to put them back together in some sort of order. So the idea being then we know that this value is smaller than this, but then we know this value is smaller than this, so we move that there. Then this value is smaller than 7, so we move that there. That's how the 3 ends up here. This value we know is bigger than the 3, so we move that way. Is it bigger than 12? Yes, so we move that way. We then end up like this. So it's dividing numbers down into individuals so that we can then compare them quicker. Rather than comparing a big list, we're going to compare individual numbers and then putting them back together at the end in a structured and sorted way. So merge sort is dividing them down from fours into pairs and then from pairs into single numbers, and that's how a merge sort works. Right, a insertion sort starts with the furthest number to the left, and the idea is we try to put it into the position we think it is. Right, now that sounds silly. So look, essentially it starts like this, but this number here, 23, is it bigger than 1? Yes, it is. So I'll try and insert it into a position that I think is the correct place. So my example then is, my 23, is it bigger than 10? It is, in which case I'll move it there. Is it bigger than 5? Yes, in which case I move it there. Is it bigger than 2? Yes, in which case I move it there. So my 23 is moved along until eventually I think I've inserted it into the right place, like that. Alright? Now we do that with every single number in the list. So then I'd move on to my ones. Do I think the one's in the right place? No, I don't. In which case I'd move it into where I think is the right place. Because it's smaller than both the values, I'd move it to the left. And it works on each individual number, trying to insert that individual number into the correct position in the list. Right, so the way you answer this exam question, so we've got to try and split this data down. Alright, what we tried to do, first thing we're doing, we need to split the data in half. Alright, so we're looking at binary search. So we're going to look for a value. We go to the middle point, which in our case is this one, pumpkin. Alright, so we've got to pick the middle number first. So the idea is we'd rewrite the list, so you'd write the list here, but make sure that you highlight pumpkin as the middle value. Alright, because pumpkin is further down the alphabet than house, we disregard this whole side of the list and then we focus on this bit. The whole mark here is essentially knowing that the binary search is about removing half of a list. So with pumpkin, that means we're going to focus on this half. We then compare the next value. So we've got rid of some comparisons here of value, which is why then we go back to the middle value again, which is somewhere between flower or house. Here, this is our next middle value, and then we compare those two. Is it equal to flower? No, so we bin that off. Is it equal to house? Yes, it is, and therefore we found the value. Alright, and that's how it works. That's your marks. You just basically need to write the different stages of the search. So start with all of them in the list, so all 5 are there. Then you remove the half, the lower half, and just explain why. Then you test the next half, so in between flower and house. Is it equal to flower? No. Is it equal to house? Yes. Value found. Right, the next one's just a really easy tick box, really. So it's true or false statements about the different uses of the different searching and sorting algorithms. So essentially all you need to do is read the values, read the tests, double check what the list, the type of search or sorting algorithm actually does. You're not even actually doing anything this, but it's 5 easy marks. So essentially, that first value is true. We then go to false and true and false. And that's really it. Just read the values, spend a minute checking, and see if you got them right yourself. Right, the Lex searching algorithm is a linear search. So all you need to know for this one is you copy out your list again of the different names, and essentially we start at the furthest to the left. It tests the value. Is it equal to that one? No. We cancel it and we move on to our next one. As long as you go each value is equal is x is what name we're searching for is it equal to this? Say, is Anna equal to Rob? No, it's not. We move on to the next one, and the idea is, does it equal the value at each point? So you test every value in the list in order, line by line. That's a linear search. Alright, so you're moving on until eventually we find the value we're looking for, and that's a linear search. One at a time, in order, linear.